In this video, we're going to talk about what happens when a function is not continuous at a particular point. What we say is that f is discontinuous at x equals c if it is not continuous. So just say here that discontinuous just means not continuous. But we also say here that c is a discontinuity of f, of our function. So when we talk about discontinuities of a function, we're talking about points where it's not continuous. Either the limit doesn't exist for one reason or another, or maybe the function doesn't exist there. And usually we'll just restrict our attention to places where the function does exist around the point. So if a function just is only defined from -1 to 1, technically 2 is a discontinuity, but that's just because the function isn't defined anywhere near 2. Usually we'll talk about ones where we actually can talk about points around that c, but for some reason c itself is a problem spot. Now the first category that we're going to look at, and this is really the only category the book really gets into that gives a name, is what we call a removable discontinuity. For an example of what we mean here, let's look at a function. Recall the function f of x equals x squared minus 1 over x minus 1. We use this multiple times for examples in section 1.5. And we found that except for x equals 1, we can simplify this function by factoring the top. That becomes x minus 1 and x plus 1. And then we can cancel out the x minus 1s. So this equals x plus 1 as long as x is not 1 itself. As long as we're not talking about 1, because 1's not in the domain of this function, to plug 1 into this formula, we get a 0 on the bottom, and that's a big problem. But as long as we're not talking about x equals 1, then we're really just talking about the function x plus 1. This is a polynomial, or we can even look at the rational function itself that has domain everything except for everything except for 1. And that means that this function is continuous everywhere except for 1. 1 is a discontinuity of f because f of 1 is not defined. We can, however, find the limit at 1. The limit, as x goes to 1, of f of x, because we can go ahead and use this formula here, we can just go ahead and find the limit as x goes to 1 of x plus 1. And this is just a line, a linear function or polynomial. We can plug 1 into that formula. We get 1 plus 1, and we get 2. Essentially, what we have here, we have this graph here. We have the function x squared minus 1 over x minus 1. Now, GeoGebra will not show us the discontinuity there. It kind of just skips over it because it doesn't try to show the holes. But there is going to be a hole at 1, 2. So at 1, the function technically doesn't exist, but it does have a limit of 2. So it looks like it should pass through the point 1, 2. It just has a hole there. We can kind of repair f by giving it the proper definition at 1. If we just say, well, at 1 it does equal 2, then we can basically fill in the hole. Essentially, we can redefine f of x to equal our formula that we already had when x is not 1, and 2, the value of the limit when x is 1. If we do that, we've repaired f, and we've removed the discontinuity. Now, in this particular case, we could actually simplify this. This whole thing is just x plus 1. Because x plus 1 equals this when x is not 1, and it equals this when x equals 1. So it's the same thing. But that's not always the case. There are removable discontinuities where we can't just simplify it down to a single formula like that. Especially when say a piecewise function. If you looked at the last example from from the previous from the previous video in this section, we technically had a piecewise function where there was a limit there at the where we had to break it up into pieces. And so if we had a discontinuity there, if we hadn't defined the function there, we could still remove the discontinuity even though we can't just simplify it down to one formula. But basically, removable discontinuities is any place where we would have been just able to just keep drawing it, but there was a hole. And we just basically fill in that hole. That's the idea here. I will also say here that sometimes removable discontinuities are a little bit more complicated. We maybe, instead of something like this where there was a hole because the function wasn't defined there, maybe we had a hole there, but technically we had a definition for the function that didn't agree with the hole. So here, what if we had used this formula for x not equal to 1, but say at 1 we had defined it as a 3? Well, 3 doesn't agree with our limit. And so technically it would be a removable discontinuity where we'd have to basically repair that wrong definition and remove the discontinuity that way. But usually that comes up when we're dealing with already piecewise functions, where we'd have something written down like this. Maybe someone tried to repair it and they just picked the wrong number. The second kind of category that we're going to look at is what's called a jump discontinuity. Let's look at a really nice and simple example of this. We'll say f of x is equal to 1 when x is greater than or equal to 0, and negative 1 when x is less than 0. Now, we actually saw this before. I guess technically here, if we left out x equals 0, if we don't have a definition for that one, we basically said here that this was the absolute value of x over x. We saw this function in the, I think we talked about this in the last section. Basically, when x is a positive number, then, well, we just have x over x and we get 1. If x is a negative number, we have the positive value of x divided by x itself, which leaves the negative from the x on the bottom. When x equals 0, we don't have a definition here, but we could, by using the piecewise definition, we can include a definition at 0. But that's not going to fix the fact that this is actually not continuous at 0. It's definitely continuous for negative numbers and for positive numbers, just because these are polynomials, they're constant functions, but it is discontinuous at 0. But this time, if we want to talk about the limit at 0, if we approach 0 from the bottom, we're looking at negative numbers in our function. Well, there we're only using negative 1s, and it's staying negative 1 the entire time. So the limit from the bottom is negative 1. The limit from the top, from the right or from the positive side, here now we're actually dealing with all 1s. They're always 1s, and so that one side limit is equal to 1. These are not the same thing. Essentially, our function, it's coming in at negative 1. Why did it make that? I had it straighter than that, and it made it more curvy. It's at negative 1 down here. Then when it reaches 0, it has to suddenly jump up to 1. That's what we mean by a jump discontinuity. It's any place where it suddenly has to make a jump from one value to another. And that's always going to happen when we have these two one-sided limits that they both exist, but they're not the same number. So that's essentially what you can take to be the definition of what a jump discontinuity is. It's where both one-sided limits exist, but they give you this, but they're both different numbers. Of course, we can't fix this kind of discontinuity. There's no number we could define as the limit here, or the value of the function at 0 that will make that limit exist, because the limit simply doesn't exist in the first place. There's no fixing this without a completely radical new function. But that's kind of just tossing away the old function and not even. I mean, that's not just giving a fixing one point. That's a much more radical redefinition. So we don't say that we're fixing it in that case. But one thing about jump discontinuities is that we're not going to be seeing these unless we have something that is essentially a piecewise function. Of course, polynomials are continuous everywhere. We already saw that. Rational functions, they're continuous on their domain, but on their domain, they will never have a jump discontinuity. There's never a jump discontinuity for a rational function. On the other hand, rational functions will have, or can have, the third category of discontinuity. You can say these are infinite discontinuities, or we could call them asymptotic. These are cases where one or both of the, well, I should probably actually say both of the one-sided limits at the point are infinite. This would be something like f of x equals 1 over x. The graph of that one looks like this. At 0, we have a discontinuity. We can't plug 0 into our function, but it goes to negative infinity on one side, and it goes to positive infinity on the other side. So this is negative infinity for if we come from the negative direction. If we come from the positive direction, we get positive infinity. Of course, here we actually can't say the limit exists at all, because the one-sided limits are different, but we can still say that we have an infinite discontinuity there. Yeah, so in some ways you might even say it's kind of a jump, but it's jumping between infinities, so we want to kind of consider that a separate category. Another example might be something like g of x is equal to 1 over x squared. So this is kind of similar to what we have drawn here, except this time we actually have the same limit on both sides. They actually go up to positive infinity. So since the limit on both sides is equal to positive infinity, then we actually have we have a limit in a sense that is infinity. Technically here, limits are finite numbers, but hopefully you get what I mean here. There's no reason in writing both the one-sided things if they're just going to give us the same notation in both cases. So these are fairly common when we're dealing with rational functions, just because whenever we have 0 on the bottom and we don't have zeros on the top to kind of cancel out, the zeros on the bottom are going to force things to become infinite. Because we're essentially taking a finite number and dividing it by incredibly small numbers, and that's just going to force that number to blow up. Now, these three cases are not the only possibilities for what a discontinuity can be. I mean, we looked at something like sine of 1 over x in the last video, or the last section. That's a completely different type of discontinuity where it doesn't exist at 0 because the limit doesn't even make any sense there. It just completely breaks. But these are the most common ones. Removable and asymptotic or infinite discontinuities come up all the time when we're dealing with rational functions, and jump discontinuities are simple enough that we have a very nice name for them, even though they only really come up when we deal with piecewise functions. I want to close out this section, though, by talking about an important theorem that the book doesn't even mention. Essentially here, rather than just talking about when a function is continuous, let's put the concept of continuity to work. We're going to talk about what we call the Intermediate Value Theorem. And this is an important theorem that has an abbreviation of IVT. Pretty standard thing to be able to talk about. But what this is saying that if a function is continuous on a closed interval AB, and K is a number between f of A and f of B. I should note here that we don't really care whether or not f of A or f of B is bigger. We just care that K is some number between them. So it might be that f of A is less than K, which is less than f of B, or it could be that f of B is less than K, which is less than f of A. Just K needs to be between them in whatever order they are. If that's true, then there is a C in the interval AB. Actually, I could even call this the open interval AB, because if K were equal to one of f of A or f of B, then we wouldn't really be talking about it here. But there is a C somewhere in that open interval where f of C is equal to K. To kind of give kind of a picture of what's going on here, let's say we have A here, we have B here, we have a value for f of A. I'm going to draw it as the lower one, not that's important here, but got to pick one or the other. So I'll go ahead and draw it this way. We have f of A and f of B. K is somewhere in between them. So let's say K is here. I'm going to draw the horizontal line at K. Now f is continuous on the interval from A to B. That means that I've got to be able to draw a curve from f of A to f of B without picking up my pen. And what this theorem is essentially saying is that there's no way to get from one point to the other without crossing this horizontal line somewhere. There has to be some place where I cross it. And we're just going to say that's where C is. That f of C is equal to that K. So in concept, this is actually really kind of simple. It's just saying, well, I can't get from point A to point B without crossing this line. But of course, it's actually somewhat complicated to actually prove. We haven't really even gotten into what the formal definitions of things are here. We didn't give the formal definition of limit, and then continuity depends on limits. But without getting into all the nitty-gritty of formal proofs here, the concept here should be rather simple to think about. But let's actually look at an example of why this is useful. Let's look at a function, or a polynomial in fact. F of x is equal to x to the fifth plus 2x squared minus 3x minus 1. One of the things we like to do with polynomials is determine where the roots are. Especially since finding roots is essentially being able to factor it as well. I'd like to essentially find out where is this polynomial equal to 0. Essentially, just set it equal to 0. Unfortunately, this is a fifth power. a degree 5 polynomial. And finding roots of degree 5 polynomials is rather complicated. In fact, I'm not even sure if there is a nice solution here. It's one of those results about algebra where we have the quadratic formula to deal with quadratics. There's actually formulas for cubics and quartics as well. But for fifth degree and above, there's actually no general formula for writing down roots of these polynomials. Now, it might be possible that this one has nice simple ones, but I'm not guaranteed a nice simple answer. So being able to solve this is not something I want to even really try. However, we can actually try out some numbers. Let's pick a nice easy number to start with. Let's put in 0. If I put 0 into this polynomial, of course these first three terms are just zeros now. The only term that I'm going to be left with is the negative 1. F of 0 just equals negative 1. Let's now look at f of 2. And I guess I picked 2 because I know where this is going. If you're doing this yourself, maybe you pick other numbers. We'll try out some other ones in a moment. But if I plug in 2, well, 2 to the 5th power, that you might have to think about that one for a minute, but that's equal to 32. Then I have plus 2 times 2 squared. 2 squared is 4. 2 times that is 8. So I end up adding an 8. Then I have minus 3 times 2. Basically means I'm subtracting 6. And then, of course, we still have the negative 1. Overall here, we just end up with a 33. But what we have here is a polynomial. And we know that polynomials are continuous everywhere. Specifically, this polynomial is continuous from 0 to 2. I mean, it's continuous more than that, but for what we're talking about here, this is what we need to know. And we know that 0 is between this negative 1 and 33. We end up with a positive number and a negative number. So 0 is between f of 0 and f of 2. That means that there has to be some point between 0 and 2 that equals 0, where f of that point is 0. Maybe let's write it this way. There's a c between 0 and 2 where f of c equals 0. There's some root. There's some root of this polynomial between 0 and 2. I don't know necessarily where that is, but there has to be a root somewhere in that interval. Essentially, what we've done here is we found out that we're down here at negative 1 when x equals 0, but then we're up here at 33 when x equals 2. And somehow we have to get from that point to that point, and we have to cross the x-axis somewhere. There has to be some crossing point. If I want to narrow down the result, we could actually pick some points in the interval from 0 to 2 and see what values we get. Specifically, I'm going to pick 1. What is f of 1? Go ahead and plug that in here. We have 1 to the 5th power is 1. 2 times 1 squared is 2. Negative 3 times 1 is negative 3. And we saw the negative 1. So ultimately we get negative 1. The fact that we have negative 1 there, we have a negative at 1, we have a positive at 2. That means if, say, at 1, we have a negative number. Somewhere between 1 and 2, by the same logic here, it's going to have a root. Well, that doesn't necessarily mean that there's only one root between 1 and 2. It could cross the x-axis multiple times, and we just don't see it. But this does tell us that it crosses at least once. Between 0 and 1, well, now we don't really have any information about whether or not it does. It could actually hit the x-axis and go positive, but then come back negative. We don't know that from what we have here. We might have to do some more testing. So this isn't really an infallible test that tells us exactly where all the roots are, but it did give us information. We know there is at least one root between 1 and 2. And if we want to kind of zero in on one of the roots, maybe we pick, say, 1.5. See whether or not that's a positive number or a negative number. If it's a positive number, then now I know that the root would have to be narrowed down to between 1 and 1.5, because we have a negative here at 1, and we'd have a positive number at 1.5. If it's not a negative, if it's not a positive and it's a negative instead, well, then we've narrowed it down to between 1.5 and 2 instead. Of course, if we get 0 at some point, then we've actually found the root itself. But that's not what we're really going for here. Here we're looking at how we might zero in on a root that's not a nice number. Now, if we're really curious about the full behavior of this polynomial, we do live in a more modern age, so we can go ahead and graph it. Let's go ahead and get rid of those. So we have x to the 5th, what was it, plus 2x squared minus 3x minus 1. This is the actual graph of that 5th degree polynomial. And we can kind of see already, if we zoom in here, that yeah, there is a root between 1 and 2. It's actually here about, I think GeoGebra will actually click close enough, and yeah, it gives us that intersection point. It's about 1.13. Obviously, it might be a little more complicated than that. It probably has more digits in there, but to 2 decimal places, it's 1.13. And we can tell from our actual picture here, there isn't a root between 0 and 1, and there's only one root between 1 and 2. There are 2 other roots. They're down here between 0 and negative 1, and between negative 1 and negative 2. If we had gone ahead and plugged negative 2, negative 1, and, well, we already did 0. If we put in negative 2 and negative 1, we might have figured out that those 2 roots existed as well. Now, this is a 5th degree polynomial. There technically will have to be 2 other roots somewhere. They might be complex numbers, but this doesn't give us all the information about this function. It just gives us what we can see. I guess technically here I can tell you right away that the other two roots of this 5th degree polynomial are complex. But all that information is thanks to the fact that we have technology here. If we didn't have the ability to just graph it immediately, that would be these would be really complicated things to find out about this polynomial. We'd have to do a lot of extra work. But the point here is that this intermediate value theorem, the fact that we know about continuity here, gives us the information that we have to do various things, to guarantee the existence of roots or at least points where a function is equal to whatever value we want to find. And that's just one of the applications we have of continuity. Now, this is the end of this chapter. This is the end of chapter 1. Technically here the limits are all new stuff, but most of the stuff in chapter 1 was review. In the next section, the next chapter, this is where we're going to get into the actual meat of calculus. We'll introduce something that's kind of based off of limits. That's why we needed limits to begin with. We're going to use those limits to define a new concept that will allow us to investigate graphs and functions more than we've already done. So I'll see you guys next week for that.